All right, so we're talking about interference, and to understand double slit interference, I guess we need to understand just what is interference itself. So let's say that we start out with a wave, and I'll try to draw these to scale. Here's one that was 3 up, and okay, something like that. And if we have another wave that's just like it, and maybe I'll make that one here, we've got a situation with two amplitudes. Okay, one's got this amplitude, and the other one has the same amplitude, we'll say. And when these two are in phase with each other, that means both of these arrows line up at the same point at the same time. It means our net result, when these things are in alignment, means you have double the amplitude. And we know that double the amplitude can mean, I guess, 2 squared, 4 times the intensity, right? If the intensity is related somehow to E squared. And if these are light rays, then that's kind of how those work. What would happen, though, if I was, say, a little bit out of sync? So this synchronization and this one now no longer perfectly meet up. It means when we look at these two arrows, let's see, this one is adding up to one that's only 2 times as high. So in the first case, you had a 1 and a 2. That gives us like a 6. In this case, we've got, looks like, a 2 and a 3, which gives us 5. So we don't get as much of a new kind of net amplitude. And remember, if these are electric field vectors, they're vectors. They add like vectors. What would happen? So here we've got a little bit of a phase. What if we allowed these to get this far out of sync with each other? And that's a situation where the top one is 3 up and the bottom one is 3 down. Or rather, this one's 3 up and this one is 3 down. We can see the net result is 0. So what we've just developed is called interference. It's just the addition of the electric field vector or the amplitude vector, whatever the displacement is in the particular kind of wave. The two of these waves, if they are at the same location at the same time, so 2 waves crash into each other and coincide, this is interference. It's just the addition of their displacements. Okay, 2 situations to consider. Constructive means these things are adding and they're helping each other. So you get something that's better than either one of them by itself. Okay, so that's additive. And the net is more. Destructive is subtractive. We're losing something. So the 2 cases that are important to us is this one, fully constructive. It's the absolute maximum case that we can get where we're taking advantage of both of these being perfectly in phase. Fully destructive is this case, when the maximum up coincides with the maximum down. So these two would net result to 0. And everything in between is a little bit of one or the other, right? Here's a situation that is more constructive than destructive. Here's one that's more destructive than constructive, and I'm not sure exactly where it is, but I think it might be somewhere here. At some other point, it's called neither constructive nor destructive. So you just get something, but it's not really much, right? And this would be adding 0 to 1, so it's exactly equal to one of the 2. Okay, something that we notice about these phases, when they're fully constructive, what's a condition? They're in phase. They're both perfectly the same wave. They're exactly lined up with one another. Here we start to see other interferences, a little bit more destructive, fully destructive, starting to get constructive again. What about here? If you make a full wavelengths difference, right? So this will be a change of 1 wavelength. This also looks like it's in phase. We've gone a full cycle and now they're still back in sync, even though one had a little bit of a head start. So we want to say in phase. That means the change in the phase between the 2 is some integer number of 2 pi. And what that relates to for us is if they're off by an integer amount of wavelengths, then they fully come out of sync and then back into sync, right? Like that, like that, like that, like that. So that's not just something we need to know. If you're constructive, you need to be differing by integer numbers of wavelengths. About fully destructive, that's this situation, right? Where you go, if this is a full cycle and we've only gone halfway, to get fully destructive, we need half wavelengths. And something we should ask ourselves, does that mean that we can just call it like this, any number of half wavelengths? What if the number is 2 or 4 or 6 or 8 or so on? That would give us an integer. So you need to be a little bit more creative on this and say, well, maybe n plus a half. That way, if this can take on any integer number, you're guaranteed that it's a half. 1 half, 3 halves, 5 halves, and etc. Okay. So where do we go from here? The double slit experiment allows these 2 different waves to get out of sync with each other by some small amount. So the way it works is we'll send a laser beam or some other kind of very highly coherent light that's monochromatic. So all the light is in sync with itself. That's what coherent means. So all the rays are doing this at the same time, right? You don't have this kind of behavior. So that's coherence, and then making it monochromatic just makes it easier to see these things because different wavelengths will do things differently, right, as they go through. So we want to take something and say shine it on a screen. And why don't I say my screen is some distance L away. When the light comes in, we see strange diffraction behavior that you've talked about or we'll talk about soon, where the light just bends around corners. And then let's say we want to go to the very center of the screen and ask what happens. This is path number 1, and this is path number 2. They're exactly the same distance, so here we expect to see something bright. That would be a maxima or a constructive interference fringe, right? So it's a bright fringe, and fringe is a fancy word of saying a spot. And we know that's true because it's exactly the same path length. They both start in sync. They'll cover the same distance. We know that they'll be perfectly in sync at the very end. Things get a little bit more strange in this situation. Let's say we're off at some angle where this ray and this ray are now a little bit out of sync with each other because one of them traveled a little bit further, right? So it gave this one a chance to kind of have to go a little bit more and then fall out of sync with the 2. And what's happening here at this location? And let's call this location, I don't know, maybe Y up the board. We should zoom in on this segment. We're going to assume that L is really far away compared to this distance that I guess we'll call D, the distance between the 2 slits. So if we want to zoom in on this box, we're going to see these things are some distance apart. We know that toward the screen is really, really far away. So an approximation that we can make, or an assumption, is that these 2 rays are pretty close to parallel. They're not exactly parallel, which you obviously know, but we're going to say that they're close enough to being parallel, where this is that angle that you travel. And if we do some fancy trigonometry and cut this at a right angle, these 2 rays are now parallel to each other, and they will cover the same amount of distance from here all the way to the screen. But this is a difference in the path length. And it's a difference that one of these 2 rays has to travel that the other one doesn't. So this is a very interesting thing for us to figure out. In physics, the change in the path length must be equal to something. So what do you want it to do? If we want it to be constructive, then we need to say that this is an integer number of wavelengths. That's if you're constructive. What if you want it to be destructive? Impose a different condition. Force it to be this. There we go. If you don't like N, I think the book also calls it like M, which actually I think is what it does do. So we'll call it M. And this will be the order number in the interference phenomenon. If it's 0, then they're perfectly in sync. If it's 1, then you've lapped it by 1 wavelength, or 2, or 3, or 4, or 5, all the way up the page on the screen. So this is the physics part. What's this part? That's going to be geometry, right? So how are we going to find this delta path length? We can say, maybe I'll get another color to highlight it. This angle, theta, is the same as that one. And you may have to go through and do the trigonometry yourself to figure that out. So what can we say? Opposite over hypotenuse is sine. So sine theta equals the opposite side. That's the path length difference over the hypotenuse. That's d. The change in the path length is d sine theta. So make this substitution up here, and now you've got 2 equations for the interference 2-slit experiment. D sine theta is m lambda, or m plus a half lambda. And this is if you want to find bright spots. This is if you want to find dark spots. And we might call them bright. We might call them maxima. We can call these dark. We can call these minima. That's your equation. That is pretty much all there really is to this unit. Things that I like to do, I always just use this formula. Because look, when I look at this and I see a 0.5 on it, I know that means it's destructive. So maybe you're working this through and you want to find out, is a problem at a location going to be constructive or is it going to be destructive? You say, I don't know. Do this version of the formula and just see what the number m equals at that point. If it's a 0.0, it's constructive. If it's a 0.5, destructive. And what if it ends up being something like, 0.4? Well, it's kind of in between, but 0.4 is closer to 0.5 than it is toward 0. So it's a little bit more destructive than constructive. It's faint. It's not dark, but it's dim. Okay, realistically in practice, what we might see, some kind of problem here where you have to measure things on the wall. So let's say that we're counting fringes and we say, hey, this fringe is located, I don't know, let's say 30 centimeters up on some wall. So it's easy for us to measure that length. Let's say it's some distance away, and what makes us happy, I don't know, maybe we'll say it's a meter away. Let's say it's 10 meters away. That's not meters. Oh, come on. 1,000 centimeters or 10 meters. And this distance is, I don't know. D can be anything we want. Let's say 1 millimeters. And what do we want to know? If we know this is a bright spot, I guess the only thing to solve for is find wavelength. What are some possible wavelengths of light? And why don't we do that? Find the wavelength. Yeah, find this wavelength that will give us a bright spot here that we know 0, 1, that's going to be 2. It's kind of an unfair question because if I didn't tell us what this order number was, it could be any wavelength. Or rather, it can be some wavelengths, right? There's more than one. Just any option that would satisfy that equation. It might be a little complicated. But if we're positive, it's going to be the number 2. This is a very solvable situation. So how might I go about solving it? I want to do d sine theta is m lambda. I can see that these are bright spots as indicated in the picture. So I'll use this version of the equation. How do we find the sine? You could say that the sine of the angle is, opposite is 30 centimeters over the hypotenuse. That's a mess. We could be a little bit more clever and say, well, find the angle first and say tangent is opposite over adjacent, and these centimeters cancel. That might be a little bit less painful. And if we really wanted to be clever, we can say 0.3 meters on the top, but 10 on the side. That's going to be a really long triangle with a very thin height. That to me looks like a small angle. That would just say tan equals sine. So if we wanted to solve it, I think we were looking for the wavelength. I've got D. I'm going to say it's tangent. I'll divide it by m to get that. So we get D tan is 30 over 1,000 divided by what? M equals 2. I really don't want to solve this, so I'll leave it to you. It should be a simple enough calculation, so find it. Just one type of problem you might be asked. Okay. I think that covers pretty much all of the interference stuff. So if we feel good about that, just an observation that we can make. The interference pattern I expect will look like this. Right? And that comes from the fact that there are regularly spaced intervals on this wall where you're constructive, destructive, con, D, and so on. So we expect something that looks fairly repetitive. In reality, you will measure something that probably looks more like this. So my question to you, what happened to these fringes? There should be one here in the real pattern, but in the theoretical pattern, they're not predicted, right? There's nothing about this equation that predicts, oh, well, at m equals 1, 2, 3, m equals 4, we're going to have an empty spot. So mull that over and consider the next section.